But if you guys want, let me know in the comments below. And what I'll do is at a later date, I will go through and I'll break down all the neural networks that I've created in this Excel sheet in a much slower manner and do a better job explaining it and be more organized with my sheet. Good morning. Quick short intro. About 8:42 Tuesday. Today we're going to be going through. I have about maybe I might be able to squeeze it, make it an hour. Going through, finishing up the paper, and then I need to open up Excel and I need to start implementing this in Excel. So what I'll do is I'll actually give myself a hard cutoff. I should be done this in about half an hour. This paper in about half an hour. And in about half an hour or so, I'll open up Excel and I'll start implementing my first RNN in Excel. I'm feeling good, feeling confident. I think we can do this. My secondary camera, just in case I need B-roll footage. Oh, is that a speck on the? I thought that was a speck on my computer. That's how old this paper is, eh? The virtual termites have already gotten to it. And now I need to take a little bit of a break because I need to post onto TikTok. Okay, about 5 more minutes on this and then we'll get right into Excel. All right, let's get into some code, finally. Excited. Did that just fail? I'm just trying to pull up my whiteboard and it's just crashing on me. Let me just quickly try to summarize what an RNN is. An RNN is how Backprop works. An example will be coding in Excel. So essentially an RNN, what it is say we have our input, and we have our black box, and we have our output. Excuse the poor handwriting. So what happens is an input comes in, it goes into the black box, and so then the black box, as many times as we need it, it will cycle that information through before you actually get the output you desire. And so, for example, let's say our first input into the black box is we're trying to do letter prediction. So we're trying to have the AI predict letter by letter until it forms the word hello. So let's say we go in and we input the letter H first, and then it'll go through. Initially there's nothing for it to keep in memory, and what the desired output is E, right? And so now H is now in memory, and so H will stay there. And now E is the next letter, so now we're going to input E into the network, and so now it's going to at least have some context, and this is how it differs from vanilla neural networks. Now it has some context. Now it goes, okay, well, I saw H before, and now there's an E, and so I'm getting a sense that the word we're looking for is hello, and so with both H and E, it will determine that the output should be L, which is correct, right? And so now it has H and E in memory. And so now the next letter is L that we pass into it. And now it goes, okay, well, H-E-L. The next word is probably going to be, the next letter is probably going to be an L again. And so then that's what it outputs. And now L goes into memory. And then you repeat again for the second L. And it's like, okay, well, hold up. I already have H-E-L, L. So the next word, again, this is on a model that's specifically trained to output hello. You can have models that are trained to help output other letters. So it might give you a prediction of, well, there might be a space here, and we'll just stop at the word hell, or we'll put O at the end to make it hello. But in this case, we're just going with the model that's only trained to output the word hello. So you input the other L, it goes, okay, well, I already have H-E-L. L is now the input, and so combined, it's the last letter that we're missing is O to complete this word, and so eventually at the very end it will output letters to form the word hello. And so that's how it works. Now when it comes to backprop, essentially all we're doing for backpropagation through time is we are just going through and we are just unraveling this neural network. So I'm going to call this, because this is what it's called, I'm going to call this hidden and then you have your output. I'm just going to pretend that's how you spell output. IH, just for simplicity. Oh, move this up just a little bit. Okay, so that's we effectively call our neural network 4 times, and so now what we want to do is we want to go back in time and we want to backprop, and we want to figure out where errors are, and we want to update the weights. Now, what's interesting is that this hidden section, so this black box that then forms this hidden section here, what's interesting is that it has a constant set of weights, so the weights never change. It's just going through, it's just looping through that same hidden layer with the same weights. And interestingly enough, because it has context and because you provide it different inputs at different times, and because it has memory, what it does is that it actually will output different stuff at appropriate times, which is pretty interesting. Now, when it comes to backprop, it's quite simple. All we really do is we just go, okay, let's start from back here, which is what I thought, and I think that blog post from Analytics Video just completely threw me for a loop. But essentially what we're doing is we're starting here, and what we'll do is we will calculate. So here is where you have your final output. Again, this is a very, very rough explanation. I'm sorry, my apologies. This is my first time explaining this. This is something I just learned, so it's not going to be the most polished. I'll work on it and maybe release another video where I do a better job explaining and going through it slowly. But this is kind of just for me to think out loud and just gather my thoughts and see whether or not I actually understand it. Because if I can explain it, I pretty much understand it. So now what we're going to do is, because we have our output, which is the word hello, essentially, or actually we have HELL, no, ELLO, because H is what we're starting with. So now what we're going to do is we're just going to calculate, okay, what produced this output, and we're just going to backpropagate. We're just going to go through the neural network. And so we're going to start from the very end because it's backprop. So what we're going to do is we're going to say, okay, we produced H at this time. So essentially it just turns out to kind of be like backprop for a feed forward neural network. That's probably a summary of what all this is, right? Because essentially it's pretty much the exact same thing, right? So it's backprop for pretty much just what is a normal feed forward, except that you are just backpropping over the same set of weights for the hidden layer the whole time. That's number one. And so because of that, so it's the same weights across the neural network, right? So you have the same weights that connect the input to the output here. You have the same weights that always connect the hidden layers with each other here. Then you have the same weights that always connect the output layers here. I wanted to fill it in, color it in like I did with the other ones. That's why I moved the mouse down here. But yeah, so it's essentially just the same weight. So what you're doing is you're just updating the same set of weights over and over and over and over and over again, until eventually, because of context and because of the way the recurrent neural network works, it starts to be able to contextualize data that you're feeding it. So pretty much it. It's like a very quick high-level overview of what it is. I have about maybe 15 minutes, so let's get into Excel. So I'm just copying basically the structure I have here. Forgive the messy nature of this book or this sheet. It kind of helps me understand things. But the way we're going to represent hello in the neural network is we're going to pretend as if we have a vocabulary set where we only have 3 letters, so four letters, HELO, and each one, and we're just going to do a one-hot encoding for each one. So if the letter is H, it'll be represented by an array of 1, 0, 0, 0. If the letter is, say, L, for example, it'll be represented by the array 0, 0, 1, 0. So that's what we're going to do. First time step, all we want to do is we want to input the letter H into the network. So let's build that in. Okay, and we're going to add our bias. Again, I'm just restructuring the code that I've already done. going to be the same thing mostly. Multiply. So we're going to have a set of weights. So let's just go through before I actually build that in. So let me just go through really quickly what the structure, what the structure of the neural network will look like. So we'll have 4 nodes for the input. Again, these 4 nodes, they just take in bits that represent the letter. Then what we're going to do is we're then going to have, just for the beginning, just for simplicity's sake, we're going to have 3, we're going to connect them up to 3 nodes inside the input layer, and then the output layer would have 4 again. And so these 4 will then represent the output, or will represent the letter that we will be outputting. So that's, I get distracted by the most useless things, but that's what we're going to do. So because we have 3 nodes in here, the matrix, the multiplication will look like, so 1 row, 4 columns. That means that the matrix size for the input layer will be 4 by, and then that will be determined, we'll determine, because this output also has to be, am I doing this correctly? Oh, my bad. No, I made a mistake. I made a terrible mistake. Wait, hold up. Should the network output, oh, okay, right. Okay, no, I actually did make a mistake. I was right, because this is a recurrent network that is essentially a, what is this, like a many-to-many type of neural network, recurrent neural network, where we have multiple inputs over time, and they produce multiple outputs over time as well. So this is known as a many-to-many type of recurrent neural network. So yeah, so for this one, we want to output, or at least in the context of our, the way I kind of built it out, which is kind of confusing and it's not conventional, whatever. But, so it's going to be a 1 by 4, 1 row, 4 column matrix. And so that means that here, in order for this matrix to be compatible with both of them, or at least multiplication-wise, it has to be a 4 by 1. So that's what we're going to do. We're going to create this as a 4 by 1 matrix. Wait, how the hell does that make any sense? Okay, hold up. Nope, I'm confused. Oh, what am I doing? No, hold up. How does this work again? Okay, so it's gonna have to be a 4 by 3. Oh, okay. Yeah, what am I doing? I'm confused this morning. Okay, that's what it was. Okay, so the connections here, because this is 4, it's gonna be a 4 by 3. These synapses here are going to be represented by a 4 by 3 matrix. So we have the 4 nodes, and we bring them into 3 synapses. We have the 4 input nodes, and then the 3 hidden nodes. What we're going to do is 3 by 4. The end here, and so then we're able to export, or we're able to output a, I think so. Let me try that out. I haven't done this in a while, so I kind of forget how the matrices should be. Let me try to re-jog my memories to how this works again. Oh, okay, right. You have your input, then you have your synapses, and they produce the, whatever your layer one, whatever dimensions for layer 1 is, and then you have, okay, that's what I was forgetting. So yeah, so then the synapses would then have to be a 2 by, let's say we want this to be 3, 2 by 3, and then this would have to be a 3 by, so sorry, this would have to then be a 3 by 3 matrix, and then you multiply this by a 3 by 1 matrix to then form a, pulling up an old notebook of mine where I've written all this down. How the hell did I forget all of this? Okay, so this is the input. You multiply it by the synapses. So then you have 2 by 3. And so, sorry, then your output would be a 1 by 3 matrix, which has to then represent the hidden nodes. And then the hidden nodes, you then multiply that by a 3 by 1 matrix, which then gives you a, oh, okay. So let's get back to here. And now I have to go to work because I've wasted my whole time trying to remember how that stupid thing works. So here, remember, because of the way we are inputting, or the way I have it structured in my sheets, it is a 1x4 matrix. So 1x4 matrix. Then we're going to multiply that by, so this is the input, and then the weights, or the synapses, for the first layer will then be a 4x3, and then that will give us a 1x3 for my, whatchamacallit, for my hidden layer. So, and then what we're going to do is we're going to then multiply that by a 3x4 weights. So the second synapse. So I'm just going to quickly go through this, and I'll explain afterwards, and I have to bounce. And so then that will give us a 1x4 matrix output. So this is the input, and then these synapses are represented by this weight matrix here. These hidden nodes are then represented by this hidden matrix here. These other synapses are represented by this matrix here, and then finally we have our output, which is then represented by this. Okay, I don't know why that simple linear algebra rule confused the hell out of me for some reason. Probably because it's in the morning and I didn't get much sleep last night, to be very honest. But okay, so then the weights are going to be a 4x3. Okay, thank you. That's what I wanted to know. So 4x3. So then we multiply it by a matrix of 4x3. We're adding 1 just for the bias, but essentially it's a 4x3, and then it'll give us a hidden node of. And so one of the reasons why I don't really worry too much about the bias is that it does not affect the final output here, because if it's a 1x5 by a 5x3, we're still going to get a 1x3 matrix according to laws of linear algebra. So here we're going to have 3 matrix multiplication of here by here, give us okay, and then with that we have our first layer implemented already. It's very slow, but we're getting there. So sigmoid is the formula for sigmoid again. Okay, now the interesting thing about this is we have to actually keep building on the same line, unfortunately. And so what I will do is I'll just keep building this out on the same line. I really have. So this is layer 1 output. You know what? Let me go to work, and then I'll figure this out later. And we're gonna have to do this. We're gonna have to do a second session in the afternoon. So see you then. Here we are, guys. It's about 7:45. Let's get right into it. There's not. I don't really want to waste any more time. One thing that I was working on in the morning was for some reason matrix math just evaded me completely in the morning. So I got very confused to how, what the size of matrices should have been. So I don't know why, but that's all resolved. Right now, what I want to really quickly do, at least build out, is the feed forward part of the recurrent neural network. If I don't get to backprop today, it's fine. We'll do it tomorrow morning. But I at least definitely want to get this feed forward done and then get the video edited as well, and catch some sleep. So let's get right back. Let's get back into it. I just need to do a quick review for me because I haven't seen this in a while. You guys have probably seen it, so no need to go over it again. Okay, so this is input. Then we have our weights. Then we have our hidden. I'm gonna call this hidden because it's more accurately represents what it is. Hidden, and then hidden activation. What I actually need to do is, I'll do this first. So let me build up this row first, and then there's one thing I'm missing, and I'll kind of explain that as we go along. So I actually need to move this. The reason why I need to move it is because This will be, so this is the raw output for the current layer. Now what I need to do is, you know what, I'll just add the rows right now. I need to account for time state 0. And so on time state 0, what we're going to have is, let's just simulate it as if we passed nothing through. And so everything will be 0. Bias, who cares, we can just leave that as is. Actually, you know what, why don't I just undo all of that I just did. Instead, just over here, I just say, I'm just going to add this to previous layer. And then this one is just going to be all zeros for now. Okay, so we add them. And now we do our sigmoid on, here. Okay, so let me just quickly walk through what I've built here. So we have our input for the very first layer. Again, we are inputting H. So in our vocabulary, where we only have 4, or our alphabet, where we only have 4 letters, we're going to represent H as that vector. We're going to add the bias to the words at the very end. That's just something that a notation that I use to just help me out. Here are the weights. We're going to multiply it through basic matrix multiplication. Ignore this stuff. This is just how I start off the or initialize the weights. I believe this is the Xavier or whatever it's called. I forget exactly what weight initialization method this is. That's that. And so when you multiply the input with the synapses, you will then get the hidden layer raw output. But because this is a recurrent neural network, what we need to do is we need to count for whatever's in memory. At the very first state, you have nothing in memory, so we're just going to initialize that to 0. I believe there are various different ways to initialize a hidden layer, but I'll just leave that at 0 for now. And then you have your actual yeah, it's not depicted in this mini diagram that I have here. But after you account for the whatever's in memory, then you have your actual hidden output, and then you go pass it through sigmoid in this case for me, which would be your activation function, and then that's your actual output. Actually, nope, not yet. So passing it through the sigmoid just gives us the output for the hidden activation. Then what we need to do is we then need to multiply it by the weights, or the synapses that connect, or the synapses that connect the hidden layer to the output. So let's initialize that right now, and let's do that right now. So this will be a, this will be a 3x4 matrix. So I can just go ahead and just copy this. I'm actually going to rename this to HT. This will be, so hidden layer in the current time step, hidden layer from the previous time step, and then this would be HT. I don't know. I'm just going to leave that as HT again. Everything is just being named to HT. Okay. And so here, what we'll have raw output. So raw output will be matrix multiplication of this guy and this guy. Oh, okay. So what I need to do is I need to manually add another bias node. So then we have mmult of this guy and this guy, and that should work. And then we have our raw output. Yep, so it should be, my whiteboard is so annoying. So 1, 2, 3, 4. Yep, it's a vector of 4 by 1. And then what we're going to do is we're going to apply our activation function. So I'm just going to go ahead and look for where I did softmax. There we are. And I'm just going to go ahead and I'm just going to copy my softmax activation. Where is it? Is this it? I believe this is it. Okay, that sums up to 1. And in this case, what we have here is we just have our outputs. Softmax. Go to 1. Okay. Okay, let me just double check I have everything, and then we'll be good to go. So what I've currently implemented right now is, again, we're passing H into the, where's my mouse? Passing H into the network. It gets multiplied by the synapses that we have that connect to the hidden layer. That all looks good to me. And then what we do, because this is a recurrent neural network, is we add the normalized, or sorry, we add the, yeah, we had the activated, we have the activated, whatchamacallit? Basically, we add whatever's in memory. So we add the output from the previous layer, that's already passed to an activation function. We add that to here, and we get the current time steps output, and then we pass it through a activation function. Then now what we want to do is we want to go from the hidden layer to final output. So we multiply it by the synapses that connect that, and then we get our output, our raw output, and then we put it through a softmax, and then we get our final output. And so now this is a probability of, if right now our network, when we pass H into it, it's telling us that, essentially what it's telling us right now is that E should be what follows H, which just coincidentally happens to be correct. It's not been trained or whatever, so it doesn't know what the hell it's talking about. It's just coincidentally happens to be correct. Let me just double check, just make sure I implemented everything correctly. Oh, okay. One thing I guess I'll have to play with, and that thing that will confuse me is, you know what? I'll cross that bridge when we get there. Getting ahead of myself. Okay, and then over here as well, what I'll just do is I will start a loss. The only thing I'm missing, and we should be good to go. So what we actually expect at this point in time is, or actually, so this is target. So at this point in time, what we actually expect is this to be 0, this to be 1, this to be 0, this to be 0, and so then our loss will then just be, because this is cross entropy loss. Let me see if I have a formula for that. No, I don't have a formula for cross entropy loss. How do I do the derivative then? Oh, I just use the, gotcha. Okay, so I think this is what the natural log is. Let's double check. It's been a while since I did calculus. Oh, right, yeah, ln. Totally forgot about that. Okay, actually, let me do this. Some product of that and that. So I'll get us, oh, okay, that's what I want. Okay, so that looks good to me. Now all we need to do is just take everything that we have here and then just copy and paste for layer 2, copy and paste for layer 3, and copy and paste for layer 4. So HELL, I think is all we need, 4 layers. So in this layer we have oh, okay, you know what? One thing I do need to change up in this layer is, so our weights stay the same. So what I need to do is actually completely get rid of all this stuff. Everything here stays the same. So it just references the weights above. Okay. And yeah, okay, so that looks good. I'm multiplying by that. Our previous hidden layer would be, now what I also need to do, just so I don't forget, is not only do I need to take this into account, so mmult, should I do this? So what I'll do is, so this was what my earlier question is. My earlier question is, what do I do with the bias in this case? Because bias is already taken into account my calculation here. I think we only need bias once, right? So what I will do is I will just multiply whatever's in the previous hidden layer without the bias. So just multiplying that by just weights themselves, it should produce the correct. Oops. Produce the correct frick. What's the error? Multiplying a 1 by 3 matrix by a 3 by 3 matrix should be good. Oh, actually, hold up. Ooh, okay. Now we're getting into an interesting part. So now, when we have our hidden layer, so for the hidden layer, what we want to do is we want to take the previous, whatever was in the previous hidden. So if this is time step t, for time step t plus 1, what we want to do is we want to take whatever's in the hidden layer previously. So we have hidden 1 by 3. We then want to somehow multiply it by the weights again, by the same weights. So weight 0. Yeah, this guy here. So weight 0. The problem is weight 0 is a 4 by 3 matrix. So how do I do this? Huh. Oh. Oh, okay, no, I think I see. You know what I missed? Okay, so maybe this is not the best, maybe this is actually not the best way to draw a recurrent neural network. So let me just draw something right beside it that might better accurately represent what this thing does and what it is. So let me say this is our input. We have 1, 2, 3, 4 nodes. And then we have our hidden layer. In this case, is only 3. 1, 2, 3. So it's the current hidden. And what we'll need to do is we'll need to pass in the old hidden. So this will be old hidden. And then we finally have our output. Our output is 4. Okay. And so, then we have like our weights or whatever between all these guys. And so our input will be for the purposes of our Excel. Actually, let me also just label them. So this would be 1. This would be the weights here would be 2. This would be 3. Weights here would be 4. Actually, no, this is not. This is not. See, whenever you build something, it just makes you realize how much you don't know. Okay, so let me put old hidden here. 1. Let me do it in a lighter blue color. So it's 1, 2, 3. Yeah, so I guess it's something like this then. So these are my inputs. Oh, this is going to be such a messy vlog. These are my inputs. And so you do your multiplications here, but then you also do your multiplications here as well. So this would be my input. This guy right here would be my current hidden layer, and then we're adding the product of the old hidden layer, and then we're finally connecting that to our output. Okay, so this will be, let me use our handy dandy colors here. So if our input is a 1 row 4 column vector, and we're multiplying it by, actually let me define a few other parameters or a few other variables here. So our input size is 4. Our hidden layer is 3 nodes, and then our output is 4, meaning that the weights that connect our input and our output will have to be a matrix size of input to hidden will have to be size of 4 by 3, right? And then the one that connects hidden to hidden will have to be a 3 by 3. And then the one that connects hidden to output will have to be a 3 by 4. Okay, now armed with that knowledge, what we'll do is, it's a lot more difficult than I thought. So our input is a 4, 1 by 4, then we multiply it by our current hidden layer. Our current hidden layer is, so input to hidden, it's a 4 by 3. So we multiply it by that 4 by 3. This gives us a matrix of 1 by 3. Okay. Now we're going to have, now this is for time 1. For time, oh sorry, this is for t. Now for t minus 1, what we have is we have this old hidden layer, so this will also be a 1 by 3, and then what we're doing is we're multiplying it by our hidden, which is a 3 by 3, which gives us another 1 by 3 matrix. And then what we do is we then add these two together. That gives us still a 1 by 3 matrix. And then that finally, that 1 by 3 matrix, let me add some more color into here. And then addition. And so then finally that 1 by 3 matrix, what we then do is we then multiply it by the 3 by 4 matrix for hidden to output. And eventually what that gives us is, eventually it will give us an output of 1 by 4. Holy crap, okay. Now we have to translate all that into Excel. You know what, I just realized I used the wrong color for this. It's gonna bug me. Should have been light blue. There we go. Okay, let's go restructure our Excel sheet. Yeah, so this is why I said I need another row above here. So what I'll do is I will just implement this, and so this will be our starting our row that we just used to start off. I'm gonna put that as 0. Put that as 0. Actually, don't need that. We don't need this here, so I'll delete that. So we have our input, multiplying it by 4 by 3. 4 by 3. Then you get a 1 by 3 hidden output. And then what we're always doing is we're always passing through the normalized to keep the weights normalized. So for this guy, your previous hidden is just yourself. Okay, all that can be gone. Okay, so in t minus 1, so I'm actually just going to call this t now. So this is t minus 1, and this is actually t1. So in t minus 1, nothing went in. Hidden output is 0. Previous layer is 0. Hidden output is 0, and I just got rid of the sigmoid activation because there's nothing. There's absolutely nothing here. Okay. So now in time step 1, what we're doing is we're taking our 4x1 matrix with the bias, and we're multiplying it by the 4x3 weight matrix here. And then what we're getting is a 1/3 raw output for the current layer. Then what we need to do is we need to take the previous hidden layer and we need to multiply it by a 3 by, oh, okay, that's what was going wrong. We need to multiply by a 3x3 matrix. Gotcha. That's the little piece that was confusing me for a little bit. So what I'll do is I will make another, oh, checker right here. And I'll actually just rename these. So we have our input, we have our who cares? Never mind. Too much work. This is our weights 2, and then this would be weights 3. Again, this is very, very messy, but it helps me understand. So apologize if you guys can't follow or aren't able to follow along, or it's just like too unstructured. But I'm actually making a lot of headway, and I'm understanding this. So, but if you guys want, let me know in the comments below. And what I'll do is at a later date, I will go through and I'll break down all the neural networks that I've created in this Excel sheet in a much slower manner and do a better job explaining it and be more organized with my sheet. But yeah. So this one would be a 3x3. I don't think I need bias for this one, to be honest. So yeah, I'll just get rid of bias there. We'll see what happens if, actually, you know what? Let me just leave it. And then I'll just leave it as question marks. Okay. So now we have our weights. Now we're going to take our old hidden, we're going to multiply it by our weights within the hidden layer, and then that'll give us another 1x3 matrix. So we're going to take our previous hidden, multiply it by, oops, matrix multiplication, our previous hidden, multiply it by our current weights. That should give us a, yeah, that should give us a 0. It's fine with me. And then what we do is we finally add the two of them together. So add that plus that. That gives us our hidden output, 1x3. And then we multiply, oh yeah, sorry. Then we take that through a sigmoid activation. So actually I should be going here because I always want the activated portion of the activated synapses, the activated But I'm too tired, man. I don't even know what I'm talking about. Okay, then we take that through sigmoid this time. And then what we do is we have that. We put it through sigmoid. And then now what we'll do is we will multiply it by the hidden to output, which is a 3x4 matrix, and that'll give us our raw output of 1/4. And then we will pass this through that makes no sense. Okay, so funnily enough, it's still E is still our recommended output. So then we have our loss. Okay, let me just quickly go through the code again, just make sure everything's implemented correctly. I'm supposed to be eating my dinner, but I'm so into this, just totally forgot. I think it looks good, man. I think this looks really, really good. So what I will do is I'll actually move these up here. The reason being is, so now when I'm copying stuff, I'm going to move these up there. Okay. So that allows me to at least save some space. Okay. You know what? Let me define these guys up here too. And then what I'll do is it's not going to work as well as I hope, but oh well. Wait, so why don't I just do this instead? Why am I copying over the weights for? Oh, you know what, who cares? You know what? That's such a small detail. I'm not gonna let myself get derailed by something like that, something ridiculous like that. Okay, so then in the second for T2, we're not going to be, see if I can pull it back up again. So T2, now what we're going to be doing is, so T1, we inputted H, we wanted the network to output E, and so E is the next character in the word, and so what we'll do is we'll then come back, we'll input it in the next time step, and hopefully we want it to output L, and then we'll do the same thing for L. We want it to output a second L, and we'll input that second L, and then we'll want it to output O. So we've done time step 1. Now let's go ahead and let's implement time step 2, where we input E. So weights stay the same. Let's go back to our little diagram over here. Right. Okay, so then in this case, our target will be, we want an L outputted. So then our, let me say old loss, new loss, total loss. Our loss is 0, and then we're just going to have to sum these two numbers up. Our old loss would be whatever this is. Then now our total loss is now that. And that makes sense because our output, our thing is telling us to output E with a very high probability and L with a very low probability. So the loss is quite high for this one. Okay, and so now we're just going to copy that and we'll just do that. What are you talking about? What? Now I'm just going to copy that and just do that twice. Okay, so that's done. One thing I'll do just so I can better visualize is I will just go ahead and I'll format. Yeah, so as you can see, our network is a little funny. It basically is just outputting E the whole time. That's fine. Oh man, okay. We finally have forward pass done. It's about 9. Should I start backprop? Let me take a stab at it for about 15-30 minutes. See where we get to. If I finish it, great. If not, I do it tomorrow morning. And I don't really think there's gonna be much loss because I think this episode already is pretty beefy and already has a lot of stuff in it anyway. So yeah, cool. Okay, backprop. Let me see if I can explain this in a way that kind of makes sense. Yeah, so essentially, now that we've rolled it out, it's pretty much just like doing backprop on a like a normal neural network. It's not really too. I'm not really expecting too many difficulties. The only thing that might trip me up is just how to backpropagate with this previous hidden layer stuff, but I mean, essentially what we just want to do is we just want to go through, so very simplistic backprop, something like this, right? So then you have your loss, you have your output, you have your hidden, then you have your input, and then you have your associated weights. Actually, sorry, let me take a step back. So we have our input, we have our, that then connects to our raw hidden, which then connects to our activated hidden, which then connects to our raw output, which then connects to our activated output. And then the activated output connects to our loss. So this is output activated, output raw, hidden, activated, hidden, raw, and then here's our input. So just in standard normal backprop, we're just going just going like that. So this would be dl over doa, and then this would be doa over dor, so just differentiating. And then this would be dor over dha. And the output, dha over dhr, and then finally dhr over di. So that's how it looks like with a standard normal neural net. Now this is going to be me trying to make sure I can draw everything correctly here. So with recurrent, we have our input. What the heck was that? Is my computer possessed? Okay, so we have our input. We have our hidden raw, hidden output. But then down here we also have another set of hidden raw, hidden output. Over here we have our output raw, output activated, and we finally have our loss. So output activated, output raw, hidden 1 raw, hidden 2 activated, hidden 1 activated, hidden 1 raw. And then we finally have our handy dandy input over here. So I know this is connected, I know this is connected. These two are connected, that's connected, that's connected, that's connected. So I guess in this one, it just goes back into 2 layers. So then we have our We have dl over doa. Then we have doa over dor. Then here we have dor over dh1a. And here dor dh raw. And here we have dh1 raw over di. Then over here we have d. It's going to get a little messy, so right beneath here we have dor over dh2a. We have dh2a over dh1r. Now this is going to get a little confusing because see up here with the normal one, you could just use a chain rule to just get rid of everything. Down here though, with the recurrent, get rid of that, get rid of that. Get rid of that, we can get rid of that. Sorry, this is H1A. We can get rid of that, we can get rid of that. We can get rid of that, we can get rid of that. Oh, okay. Yeah, and so then this is where the back propagation through time comes in, because then this would also be, this will also then have its, gotcha. This will then also have its, oops. This will then also roll back to, okay, well, what were its inputs, right? And then what was its own hidden, well, what's its own hidden, you know, like negative, like, yeah, it just gets deeper and deeper and deeper. So, okay, so I'm still a little lost as to how the chain rule applies to here. I think it's much more complex than I would want to sit down and go through. So what I'll do is, I think I pretty much understand it from like a very high level. I guess where my confusion just comes from is what happens when you're at this fork. And I think it will just be very tedious and time consuming to just go through and try to, you know, figure out the proof for it. Especially because there's like multiple, we have multiple different layers. It's like 9:30 p.m. I really don't want to do this. So what I will do is I will just implement the code in Excel form, and at least hopefully through that implementation, I'll get a better understanding and things will finally click. If not, then at least I see how it works under the hood and I at least know what's going on. That's at least valuable too. So I think I'll stop it there. I think there's already a lot of content to go through, and this episode will just be way too dense. So, and I just really want to edit and just go to bed, to be very honest. So I'll stop it there. I'll implement Backprop in Excel tomorrow. I'll see you then. Thank you guys for watching. Let me do a proper intro. Look at the camera. Thank you guys for watching. Sorry, I got distracted by something.